he will talk about this finite density holographic network.
All right. It's a real pleasure to be here. I would like to thank the organizers for inviting me to such a wonderful workshop and the program. And I will entertain you, hopefully, with some comments on holographic matter states. So I'm going to make some disjoint comments on finite density strongly interacting states. And my collaborators listed here, some of them in the audience. And there's also some related work by Andrei and collaborators, and Bill and collaborators, and other people. So let me start by a brief introduction. You're probably all aware that generally physics at low energies is described by effective field theories. And there are lots of examples. Essentially all theories in particle physics is of this type. Hydrodynamics is of this type. And of course, Fermi liquid theory is a good example. Now, it would be nice to have a description of theories at finite density, some kind of effective description of theories at finite density, which I describe by holography. And at the moment, I'm not sure if we have a good effective description, although we know quite a bit about the responses of the system. Now, of course, one interesting avenue to explore is the situation where you have strongly interacting fermions at finite density. And there has been a lot of work in this direction. So one direction involves placing fermions directly in the bulk and considering back reaction. But this is not what I'm going to talk about here. I will instead do with gravity without fermions, or equivalently, I'll try to understand the point before back reaction starts, which is n equals infinity limit from the field theory. So here's the plan. I will first talk about first half of my talk is going to be mostly about entanglement, and there will be entanglement associated with Fermi surface, but I'll make some comments on how entanglement can be useful for other things. And then the second half of my talk basically has two parts. I will talk about some interesting facts which come from holographic models, basically some measurements that we can do on the holographic models. And then I will compare these facts with some corner of parameter space of a Fermi liquid. And interestingly, things will agree. But at this point, I'm not going to make any far-reaching conclusions. So let me remind you what entanglement entropy is. And we had quite a few talks last week, so the reminder will be very brief. That's actually a very nice quantity, and the way to define it is to start by considering a Hilbert space, which is a product of two Hilbert spaces A and B, basically two systems, and the reduced density matrix of A is obtained by tracing over all degrees of freedom of the system B, and the entanglement entropy is just the resulting by Neumann entropy of this density matrix, of this reduced density matrix. So in particular, it measures how the total state is entangled, and for product state, we get zero entanglement entropy, or for non-product state, we get the finite entanglement entropy, even though the state is not pure. And this can be easily generalized to field theory. All we need to do is to divide the space into two complementary systems and do the same exercise. compute the trace over B, compute the Van Neumann entropy of the reduced density matrix, and we get entanglement entropy between A and B. So this quantity is divergent, it's UV divergent, and the leading term is usually given by the area law, which is written here with the right power of the cutoff. So I guess this formula is correct for 2 plus 1 dimensional field theory. So here epsilon is some kind of UV cutoff which has dimensions of length, and so this is the general formula, and in 1 plus 1 dimensions the entanglement entropy of an interval can be computed exactly in the conformal field theory, and the result is just this. So the useful things about this quantity is that it's proportional to central charge, and it has a log L in it, and in principle now one can use it to define the C function on the space of theories. So it's not going to be the homologic of C function, but you can use unitarity to show that the C function is actually going to be decreasing along the RG flows. And something similar can be done in 2 plus 1 dimensions as well.
What is it?
L is the length of the interval. So you, as I mentioned, you divide the space into two subsystems. One has length L, the other is the complement, and then you compute the entanglement. Now, as I think we heard last week, something interesting happens when we have a system with a Fermi surface, which roughly represents a collection of decoupled 1 plus 1 dimensional massless fermions at each point of the Fermi surface. And therefore, basically from each point of the Fermi surface, we get a log. And then we have to sum over all area of the Fermi surface. That gives us this nice factor proportional to K Fermi squared. And this formula, I guess, is written for 3 plus 1 dimensional theory. And this log violation has actually been observed numerically.
I saw the right screen. You get kind of proof in it also for the Fermi?
Well, that's a good question. This formula, actually, there's not complete proof. It makes a lot of sense, and I would say it's a good physicist proof. But it's also good to check if it's really true. And I think there have been checks, like direct numerics checks.
Andrei, when you say that it's been confirmed numerically, can you say a little bit more what exactly was computed? In what sense?
Yeah, I don't remember how people. Well, okay. So usually, I think Renyi entropy was actually computed. So people basically used the replica trick and computed Renyi entropy for n equals 2, partition function for n equals 2, and observed that it has this logarithmic behavior. And I think there are also arguments that for Renyi entropy, you're supposed to have exactly the same logarithmic violation of the area law. So that I believe is what was done.
Yes, I do remember early on, right for the Fermi gas, it was started, that people wrote down closed expressions for it. I guess you have to do a numeric integral or something. I perceive this really, for the Fermi gas, really an analytic proof in essence, and for the Fermi it's a bit more tricky perhaps. The interaction. Anyhow, you know what it is.
All right, so now, of course, there is this great description. This is actually a complicated quantity, this entanglement entropy. Even computing it for free theory is a non-trivial exercise. Like if you want to compute it, for example, for free boson, you really have to do a lot of work. And generally have to do it numerically. So, for example, one paper where the area law was rigorously established was a paper by Srednicki, where he computed numerically the entanglement entropy for a sphere. And then people worked harder and found subleading terms. So in particular, there are some logarithmic terms, this quantity, which are related to conformal anomaly of the theory. So in general, it's hard, even for free theories. But now we have this holographic technology, which passed a lot of checks, and again, there are some there is even a physicist proof of its validity. So it's natural to apply it in various circumstances. And let me remind you that the prescription is very simple. So if you have Einstein-Hilbert gravity in the bulk, then what you're supposed to do is find a minimal surface. So you're computing entanglement between some subspace on the boundary and its complement. So the entanglement surface, let's say, is given by this dV, and then you're instructed to find the minimal surface in the bulk, which minimizes this action and approximates this entanglement surface on the boundary. And the overall coefficient in this quantity comes from this Newton's constant, and it's proportional to number of degrees of freedom squared. Now let me talk about some particular background, which is quite interesting. So this background describes n equals 4 superion Mills at large coupling and at finite temperature and density. So as you remember, n equals 4 has 3 commuting U1 charges, and we're going to concentrate on the situation where 2 of these charges are non-zero and equal to each other, and the third is 0. So in this case, this background has a peculiar property that the entropy vanishes linearly at small temperatures, like it does for a Fermi liquid, for example. And once you do dimensional reduction to 5 dimensions, so this background is known, the whole 10-dimensional metric. So once you do dimensional reduction, you end up with something which is conformal to a DS2 cross 3, with a conformal factor being this. And the actual black hole corresponds to alpha equals 1/2, but we can consider other metrics of this type as well, because they're interesting. They represent a certain limit of hyperscaling violating geometries that we heard about last week.
Which means alpha equal 1 is the value you get for this.
So then we do the exercise. The entanglement functional. So we parameterize entanglement surface as a function of a radial direction. So z as a function of rho is a relevant function. So this is the action. Here's the equations of motion. And I guess one thing that I forgot to tell you is that this formula, the metric that I showed to you on the previous slide, is actually a near horizon metric. It's not the full thing. So at some point, as you approach the horizon at z equals 0, at some point as you approach the boundary at z equals 0, this metric starts deviating from this ADS2 cross R3.
One question. So for alpha different from 1, can you get this type of metric from some Einstein equation?
I think so.
And do you know what that means? What type of, what is the physical meaning of alpha different from 1? So you said that alpha equal to 1 is a black hole, but the other values are...
Well, you can get other black holes too.
But
You can always complete that metric.
The difference between alpha equals 1 and alpha not equals 1 is that for alpha equals 1, this actually corresponds to
alpha equal to
black. This corresponds to finite density, finite temperature state
Yeah.
in n equals 4 superior Mills.
yeah, this is a...
While for alpha not equal to 1, you don't know the field theory dual of the resulting metric, so that's the difference.
But from the gravity point of view, you understand.
From the gravity point of view, yeah.
And so usually you get it from Maxwell-Einstein dilephancy. And I guess this one is not quite a Maxwell-Einstein dilephancy.
No, this one you also can get from.
Okay, yes.
Actually,
No,
I'll-
there's an explicit
This
mapping
Yeah, I will show.
of black holes to dilatons.
Yeah, I will show you Lagrangian for.
You will get other values of alpha by including in your higher dimensional spacetime the appropriate key form.
Okay.
And then you would reduce along all legs of that P form except 2, so that you're left with a 2 form downstairs, which is your U1 gauge field. That would give you a whole range of alpha. And this would still correspond to some like supergravity-like effective.
But you don't know what the field theory dual of this is, right?
Well, it would be like the D3 or the M2 or the M5 brane, but not rotating. Because in your case, this one is rotating, right? And these are the U1s.
You can't get a generic alpha from a D3.
No, not from the D3. But
So you don't know what the field theory dual is in general.
you would know what it. No, not in general, but you would know for specific points.
Oh, for a few, yes.
No, I agree, not in general.
All right. So it turns out, however, well, this equation, that equation of motion that you get for the surface, is looks pretty bad, but you can actually analyze it, as it turns out. And one interesting fact is that the solutions do not approach the boundary for a finite value of rho. So you can start with some, cup-looking solution. Then, as you approach the boundary, it just goes like this. So it never wants to get to the boundary. Then you say, well, how am I going to compute entanglement entropy of a sphere? So what happens here is, as I mentioned, this is a near horizon metric. So at some point, as you approach the boundary, the full black hole metric kicks in, and that sort of guarantees that your entanglement surface in the bulk approximates a spherical entanglement surface in the boundary. So here are some facts about the solutions. So you can do numerics, of course, but it turns out that the leading term you can even extract analytically, and the result of both calculations is that you get. So the interesting fact about, again, there is this interesting question in this holographic calculations of entanglement entropy, which is related to a quantity called topological entanglement entropy. So topological entanglement entropy is defined in 2 + 1 dimensional field theories with a gap, and it tells you whether the ground state has long-range correlations, which cannot be detected by local operators. Now, it would be interesting, of course, to cook up a system in gravity which would exhibit such a behavior. And of course, naively, the way you do it is you just compactify one of the directions so that the system develops a gap, and then you compute, you compute entanglement of a disk there. And if you have non-trivial topological entanglement, this disk is supposed to have some constant term. But generally, if you do something like this, something that I just said, the entanglement surface for sufficiently large value of the radius just breaks, and it becomes disjoint. So before it was this had the topology of a disk in the zero plane, and now it has a topology of a cylinder with a hole. So it's actually nice when you have a surface which always has the topology of a disk, no matter how large this radius is. So that's why this metric is nice. And I was hoping for a while that it's going to naturally give this topological entanglement, but that's not the case. So you just get the area. Well, this of course is a formula in 3 + 1 dimensions, but in 2 + 1 dimensions things are very similar. You also get the area law and nothing else.
So instead is the constant drops out, you can do an expansion in the area, and then you just
That's right. Well, there are some thoughts of how one may engineer such a constant, but we're not going to this.
These metrics for generic alpha, you think you can get them from some Einstein-like gravity?
Yeah, we just.
They are in Einstein frame.
Well, yeah, we just discussed this. Yes.
And so what you're saying is that for large values of the radius, then the surface just falls directly through the horizon. It doesn't connect before falling through.
No. So that's the other way around. So let me repeat what I just said. So in the naive holographic duals of systems with a gap, where you have geometric confinement, where you basically take an Nichols-Sauceprian Mills, compactify it in a circle, zero temperature. You have a geometric confinement. The circle shrinks to zero size at some point. Now compute entanglement entropy in the resulting 2 + 1 dimensional theory. compute entanglement entropy of a disk. When this disk becomes sufficiently large, larger than the size of this compactified circle, which also sets, of course, the scale of a gap, the entangling surface stops being connected. Instead, it just smoothly ends at the point where the cigar ends. So that's what happens there. So there, because of this geometry, you cannot have a constant term. So here, the situation is different. And here, it's quite the opposite to what you said. The surface never gets to the horizon. It's always like this. So it always has the topology of a disk.
So those geometries, you wouldn't call them gap, right?
Which ones? This?
Your alpha geometries.
Yeah, right. Well, if you compute there's a scale in them.
Yeah, but it doesn't make them gap.
So if you compute the two-point function in these geometries, large distances, what we're going to see?
For instance, if you compute the optical conductivity, you find some power law at low frequencies.
You set specific heat or entropy because of temperature, right?
Yeah.
Very gaps. So.
All right, yeah.
Right, so it's just kind of strange. The entanglement surface cannot really dip in the horizon. It sort of approaches very closely, but because of the hyperscaling, it stays away from it. Right?
That's right.
Yeah.
Because otherwise, in ADS 2 cosine 3, it would fall through, right?
Well, in ADS, ADS 2 cross R3 is basically a new horizon of Resin-Ostrom black hole.
Yeah.
So there, of course, if you compute the entanglement entropy for sufficiently large areas, volumes, you're supposed to pick up just the ground state entropy of the black hole. So it will not come through the horizon, but it will hug the horizon. You'll get the volume behavior. So while here you don't get the volume behavior, you get the area now. But the truth is, the hope was that perhaps this thing could exhibit logarithmic behavior somehow, but no, it doesn't work this way. So, okay, let me just summarize this entanglement story. So there's no logarithmic behavior here. One interesting fact is that there's no phase transition. So as I mentioned, in these geometries with confinement, you have a phase transition but as you vary the size of your entangling surface. And also we heard some talks like last week on this subject. So there was this interpretation of this phase transition as being a Hagedorn-like phase transition in field theories. So here we don't have anything like this. So I already talked about topological entanglement. And I should mention that there are some nice papers by these guys who did engineer a metric with the logarithmic violation. And I will talk about it later. Any questions?
Do you expect that you should be able to see a topological entanglement entropy geometrically ever?
That's a good question.
Yeah,
I don't see why not.
Okay, so but are there examples where it's really large in the large n limit?
Not that I'm aware of.
Okay, but okay. But even in field theory as well, there are no examples like that.
Well, as you know, it's not so easy to compute entanglement entropy in field theory.
Right. There are lots of formulas though for time
Right.
and things. Do any give you something large in the large n limit? Or?
Yeah, it's a good question. Yeah, I'm not aware of this actually.
Okay. I can never quite
do you know an example of this?
Not really. Whenever I take the large n limit, I don't know quite how to take the large n limit, I guess, in those formulas. But doing it naively, I seem to get funny things like log n or things like that.
All right.
So I wasn't quite sure.
Actually, I will have some comments related to this discussion.
Okay.
So
Okay, great.
You said that for the sphere case, there are no phase transition, but for the belt case, you have the phase transition.
yes,
Is the final temperature or zero temperature?
this is all zero temperature.
Zero temperature.
Yeah. So in QCD-like theories, you have phase transition for both. And here, you have phase transition for the belt, but not for a sphere.
That's change.
All right. So let me now sort of slightly change gears and talk about Fermi liquid. And I guess here I don't even have to remind anyone that the defining equation for Fermi liquid is basically this expansion in the change of the distribution function, and this is how the energy of the system changes. So here this epsilon defines the dispersion relation, and the useful quantities are Fermi velocities, which is just the derivative of this epsilon with respect to k at k Fermi, effective mass, which is very naturally defined this way, and the interaction between quasi-particles, which can be taken to live on the Fermi surface. So this interaction, in the end, boils down to this function of the angle between 2 points on the Fermi surface, f, and if you expand this f in Legendre polynomials, you end up with a bunch of Landau parameters. So these are the quantities that are going to be useful. Now, these quantities are interrelated in some way. So in particular, there's a formula for effective mass, and there's also a formula for the speed of the usual thermodynamic sound, which is called U1 here, in terms of F0 and F1. And then, of course, there is this important fact that at small temperatures, heat capacity of a Fermi liquid scales linearly in temperature, and the coefficient is just proportional to effective mass in k Fermi in 3 plus 1 dimensions. So an interesting dynamical property of Fermi liquid is the existence of a gapless excitation at 0 temperature, which is called the zero sound, and the speed of zero sound, s, which is a ratio of the speed of zero sound to Fermi velocity, can be determined by solving this integral equation, where this nu parameterizes deformations of the Fermi surface, and in some simple cases it's actually easy to solve it. For example, when f doesn't depend on the angle, you can actually solve it exactly. So one can also find this zero sound excitation by summing all the bubble diagrams. So suppose you have three fermions with some interaction. So then the correlator is just given by this, where chi is the one loop diagram, and the spectral density of this 2-point function is just the imaginary part of this correlator. So it's given by this formula. So in particular, there is a pole in delta function-like pole in this expression, which happens when the imaginary part of chi naught vanishes, and this thing also vanishes. So you can do some exercises with the spectral density, and these exercises, the results of these exercises are plotted here. So here, for example, you have a sound pole, and this is the Landau particle Hall continuum. And here we plot what happens as the spectral density. Sorry, as the here we talk about the simple situation where we have only one Landau parameter of naught, which is large. And the interesting question is what happens as you take it to be very, very large. So if it's small, then the Landau continuum more or less close to the pole. But as you take it to be large, this Landau particle Hall continuum gets more and more disjoint from zero sound, and in the end just pushed away to this omega equals 0 axis. So the end point of this is that if you have parametrically large Landau parameters, you're supposed to see only the zero sound pole and nothing else in the spectral function.
What's the physical meaning of this F0?
Well, it specifies the angle-independent interaction between the quasi-particles on the Fermi scale.
There's a compressibility.
So here's the formula that you get for the speed of zero sound from this condition that I mentioned, and you get precisely the same formula from this integral equation that I showed you a few transparencies earlier. So the interesting fact about this formula is that in the limit of small interactions, there is a difference between the speed of thermodynamic sound and the speed of zero sound. The speed of thermodynamic sound is, of course, well, suppose we're in the conformal theory, so the speed of thermodynamic sound is just dp by d epsilon. So it's just this. So in 3 + 1 dimensions, 1 was square root of 3, while the speed of zero sound is given by the Fermi velocity. So this ratio is different from 1, while in the opposite limit, when you take the Landau parameters to be very, very large, this ratio approaches 1. So again, this zero sound is not, it's a gapless excitation. It's not a hydrodynamic mode in the sense that even its speed is not given by the usual thermodynamic formula, which must be true for any hydrodynamic excitation. But when you take Landau parameters to be sufficiently large, its speed is equal to the speed of the normal sound. And also, the upper edge of the particle-Hall continuum is defined by this formula. So it's separated from the zero sound when there is this hierarchy, when the speed of zero sound is much, much larger than the Fermi. So, how much time do I have? Okay, so well, some simple examples where you observe zero sound involve D3 brains and probe brains which intersect them. So it was this excitation was originally discovered by Andrei and collaborators, and generally it exists for essentially any brain intersection. And the interesting fact about maybe I should mention to you just a few words how the holography is done in these cases. So when you consider holography for probe brains, you consider the 3 brains at large n, large Stoft coupling. So you're in back-reacted geometry. You put a probe brain in this geometry. Finite temperature corresponds to asymptotically idealized black hole. Finite density corresponds to gauge field on the probe brain. And you can compute things at 0 temperature and finite density. For that, you need to identify proper gauge invariant variables on the probe brain. The relevant action is just a dBi action. So you do this exercise, and you have some differential equations of this type, which you can solve, and in the end, you end up with dispersion relation, which is dispersion relation for a sound mode. So this is the result in 2 + 1 dimensions, but you basically get the sound mode in the current correlator all the time. And the interesting fact of the sound mode is that, well, here is the exercise done for massive hypermultiplets added to an equal source of Rand Mills. So here things also depend on the mass. So no matter what you do, you always end up in a situation where there is a sound-like mode, and its speed is equal to the speed of the usual sound, the thermodynamic one. So that's an interesting fact, and as I mentioned to you before, from the Fermi liquid theory point of view, this is what happens when you take Landau parameters to be parametrically large. So now let's go to this two-charged black hole, and there are some thermodynamics facts. The heat capacity of this black hole is linear in temperature, and you also know what the density is. So now let's assume for a second that we have Fermi liquid theory description of it, and the Lagrange theorem applies. So this allows us to fix K Fermi, the effective mass, and V Fermi. So the interesting fact about these quantities is that K Fermi is parametrically large compared to mu, and V Fermi is parametrically small. So in particular, the fact that V Fermi is parametrically small is in line with the statement that you don't observe any particle-Hall continuum, and the only thing that you see is the zero-sum mode. Now you compare the expression for the effective mass, and you get the following result for F1. So F1 actually diverges, it becomes very, very large. And one can actually solve, well, using some approximations, solve this integral equation for the speed of zero sound. That's a more or less standard technology, which is explained well in this review by Abrikosov and Khalatnikov, I believe. And you basically have to solve some matrix equation. So if you go through the song and dance, you solve this equation and impose this observational fact that the speed of zero sound is equal to the speed of the first sound, you end up with the statement that F2 is equal to -5. So that's an interesting relevation from this exercise. So now F2 is equal to -5 is actually a stability bound to a Fermi liquid.
So you assume here, right, that you can terminate the expansion at F2. How can you be sure that they don't have to worry about F infinite?
Almost. I assume that F2 and larger, well, actually, yeah, I assume that F2 and larger are all over the 1. That's the assumption.
Yeah, that's an assumption. Yeah, you cannot quite exclude some divergence in that when the problem.
Yeah. So now,
I just think it would be very good.
so now, let's see what it means for other variables. This time.
Andrei, can you go back 1 second? It's an expansion for small s, no?
Yes.
So how do you cancel the 1? All the other terms are ordered as squared.
Oh, because F1 is divergent.
F1 is the I put like it's not divergent like 1 over s.
I think it's divergent like 1 over s squared.
I get this right. It's pretty much like a canonical heavy Fermi liquid as experimentally see it in the uranium S compound. Or are they so different?
Yeah, possibly. So let's now see what the observables are. So if you believe this Fermi liquid description. So one interesting fact is that K Fermi is parametrically larger than mu, which means that we cannot see K Fermi in our usual 3-level gravity computations. And now I don't know how we can see it. The other thing is that V Fermi is parametrically small, so we're not supposed to see particle-Hall continuum, and that is indeed true. Only a zero-sound pole appears. Now, as far as logarithmic violation of entanglement entropy is concerned, if we go through the n counting, we are supposed to, the logarithmic violation is supposed to have a factor of n to the 4/3 in front of it. And of course, that cannot be seen at tree level. Now, two questions. One is, how can you get such a power from the usual n counting? But of course, at finite density, interesting things can happen. And the other, can one try to see a subleading term in entanglement entropy?
Oh, no, I get the fact that the mass analysis is just that you basically argue that it's like an effectively infinite mass thermal liquid, right? In the
Well, yeah.
Yeah. And now I look at the mass and I see that you said it goes like n squared to the power 2/3. In other words, it's like a large n effect because n tends to infinite. But you have the infinite mass analysis.
That's right.
Right. And then you argue you go to finite, then it could be that it turns into a finite mass thermal.
Yeah. Now, another interesting observable that one may consider is the zero sound with azimuthal dependence. So the zero sound that I was talking about before, it didn't have the thermosurface deformation, didn't behave on the azimuthal angle between the propagation direction and the position in the sphere. Now, if you consider possibility of azimuthal dependence, you can again write down an equation for the speed of this zero sound, and this is the equation, whereas one, I think, is a ratio of the speed of this azimuthal zero sound to the speed of the zero sound that we discussed before. The point is that when f2 is not equal to -5, you are supposed to observe such a mode. But precisely when S2 is equal to -5, and you take this thermal liquid to stability mount, this mode disappears. So
There should be the instability point.
So it's also nice.
So when f2 gets less than -5, I expect an instability.
That's right. Yeah, that's a good question, which don't know.
Which really is like a pneumatic instability or something, right?
Well, it's basically zero. Yeah, it's basically the zero sound mode develops a pole in the lower half plane.
Okay.
So, but
f2 is about azimuthal dependence. That's how you think it was before on the Fermi surface.
No. The instability, I think, appears in the usual zero sound. You don't even have to have azimuthal dependence for it to appear. So another useful quantity that we can look at is quasi-particle lifetime, which we can compute. And this quasi-particle lifetime enters the transport coefficient. So in particular, for generic Landau Fermi liquid, it's a fact of life that the ratio of 8/s behaves like 1/t cubed. Basically, the Fermi, the quasi-particle lifetime behaves like 1/t squared, viscosity behaves like quasi-particle lifetime, and entropy behaves like temperature. So of course, for generic gravity theory, as we all know, 8/s is just 1/4 pi, no matter what else you put in there, dilaton or other things. So it's clear that generic gravity cannot describe. It's clear that the models with Einstein-Hilbert gravity cannot describe generic thermal liquids. However, interestingly enough, for f2 equals to -5, the coefficient in tau becomes parametrically suppressed, because there is a coefficient there which is precisely proportional to f2 plus 5. So precisely for this f2, it's possible. The leading term in 8/s vanishes, and it's possible to have such behavior. So there are a few interesting things. That's
a question on that. I would be tempted to say that in the deep infrared, you should write for eta/s in the Fermi liquid the enormous Fermi energy cubed divided by T cubed, instead of the bare Fermi energy, which is mu. Is that the reason that it's suppressed, that you send the Fermi energy to 0 and therefore you lose it, or is it just different? I don't quite look through the f2.
Yeah, maybe you're right. Just open the book.
Yeah.
Go through the formulas.
And remember that f2 is in the mass, right? That is Also for the mass announcement.
No, the F1 is in the mass.
F1 is
What
in the
sits in
mass,
F2 appears in this
Okay, F2,
in this interaction.
So this eta of S 1 over t to the cubic is calculated in gravity calculation or where?
Well, so 8 over s proportion to 1 over t cube is what you expect from a generic thermal liquid. If you take, usual lambda thermal liquid with some arbitrary parameters, you must have this behavior. Basically, your viscosity should behave like 1 over t squared.
Measured in helium shui. Very famous.
But of course, in Einstein-Hilbert gravity, this is not something you can possibly get, because for Einstein-Hilbert gravity, 8 over s is 1 over 4 pi.
This is true for a billion gauge field, right? 1 over 4 pi. If you include not a billion gauge fields, then you can calculate that. Right?
I don't know. Non-abelian gauge fields.
Chinese value or making it temperature dependent?
I think making it
Okay, well, that sounds interesting. And finally, the question is when the hydrodynamics is applicable. So generally, hydrodynamics is applicable when omega tau is much smaller than 1, or equivalently, omega is much smaller than t squared. But if you have this, so this is a general statement about generic thermal liquid again. But in our case, for our specific thermal liquid, there is an extra parameter which vanishes as f2 is taken to -5. So the prediction for this specific thermal liquid is that hydrodynamics is supposed to be applicable all the way to 0 temperature. And at that point, the zero sound sort of merges with the normal sound merges with the zero sound. So we actually tested this in the case of two-charge black hole in the holographic model, and indeed that turns out to be the case. So hydrodynamics is applicable all the way to t equals 0. In particular, that's why the speed of the sound mode is actually equal to the speed of normal sound, because it's normal sound all the way. So the way we did it is we looked at low energy excitations at finite density in this regime. So now omega is much larger than the temperature, so naively you would think that hydro should not apply. But chemical potential is much larger than any other scale, and at least the leading dispersion relation is described by hydro. So again, this is consistent with thermal liquid theory with these finely tuned parameters. So of course the natural question is whether we can engineer a gravity dual with 8 over s, which behaves like 1 over t cube, and it looks like the answer is yes. All we need to do is to add a certain Dalton-Gauss-Bonnet term to this original gravity action. So I promised you gravity action, which gives rise to this black holes, and here's the Lagrangian. So if you add now to this Lagrangian this Dalton-Gauss-Bonnet term, particular exponent, we are going to get 8 over s behaving like 1 over t cube.
It's fine tuning, right?
Yes.
Yeah. Works for one specific
That's right.
gamma.
Yes. So let me summarize. Studied entanglement entropy for particular geometries and found the area law, and also observed that thermal liquid with fine-tuned parameters is consistent with essentially all the data, modulo some caveats. Then it's interesting that for other finite density states, like D branes and RN black holes, we also observe a similar situation, that hydrodynamics seems to work all the way to 0 temperature. And well, one question that is natural is whether there is a gravitational model, which really, if you take this whole story seriously, whether there is a gravitational model where the sound excitation is not the hydrodynamic sound. And if there were such a model, one would be able to see how the sound excitation interpolates between the zero sound and the hydro sound as omega varies. And we make some first steps in this direction by considering some particular high derivative gravity. Now we observe that it gives the right behavior for viscosity. Now the question is, what's going to happen to sound mode once these high derivative terms are taken into account? Thank you very much.
I thought that in all weakly coupled theories, the viscosity was parametrically large in the coupling. Is that correct? Or
At zero density.
so at finite density, this isn't true. Like you say that for Fermi liquid, it goes like mu cubed over t cubed. But so that's not parametrically large in some weak coupling approximation.
There are these Landau terms involved. Just be careful there.
Right. So is there 1 over some Landau parameter in that?
Yeah, there must be some interactions there. Yeah.
Okay. But we can take those to be order 1 in the Fermi liquid expression, though.
Yeah.
So you wrote that down, and you have the prefactors, right? The ratio of Landau parameters, and then you say I tune f2 to -5, and then I see that it's always sitting there the prefactor, and then you lose the 1 over t squared, I guess.
That's right.
Yeah.
I see.
And then f2 is transport H Landau parameters, I recall. It's not quite having Fermi liquid, it's also the stage in the transport. That's basically by the forming the Fermi surface. It also do strange things there, but I'm not quite sure what it means.
I just find it surprising that you can take the prefactor to be order 1 within the Fermi liquid theory. I would have thought that it would take you outside the Fermi liquid theory, having the prefactor order 1, because I'm imagining it 1 over the interaction strength. But I guess my real
It's a ratio of interaction strength, if I remember.
Okay.
Any other? I have one question, and I guess it's some motivation part. I guess that the Fermi liquid picture should be valid only in the very small coupling region mostly. And why in gravity, which is relevant for strongly coupled case, why you wanted to find the Fermi liquid in gravity theory?
So when you say that Fermi liquid is valid at strong coupling, I guess what you're really saying is that Fermi liquid is valid at very small energies, because it's a natural effective theory at very small energies. So I don't think anything prevents me from finding some theory like this at large Tuft coupling.
So you think that maybe very large density limit, maybe things can be like weakly coupled, so that there you want to find.
No, it's effectively weakly coupled because of the geometry of the Fermi surface. Basically, the only two terms that are relevant for the dynamics of quasi-particles, very close to the Fermi surface. So, it's a natural effective theory.
Is there any example where you really find the geometry which is describing Fermi?
You mean holographical?
Yeah.
Well, if there is an example, this might be an example.
I mean,
it's too weak, you know. Is there sort of a striking point that the conspiracy of the Landau parameters all works in the description? But to really prove that's controlled by a Fermi surface of only the fast particles, right, you have to compute directly that Fermi surface.
Oh.
There might be other ways of getting it.
Well, I agree with this. I'm not. Nowhere in my talk I said that this gravitational model describes a Fermi liquid, but no. It's interesting. It's interesting that some observations that you take from this Fermi liquid with finely tuned parameters are reproduced in this gravitational model.
But I guess it should appear as a very stable fixed point in order to be useful rather than some fine-tuned.
That's a good point.
I think this is a beautifully singular point of a Fermi liquid. I mean, it's and then surely not a Fermi liquid, completely unstable, but an other argues that is a one-of-n correction that actually about you stabilize it. It's heavy, it's 30 stage of its f2 is -5, and you have a consistent type of explanation. And Yeah, suggested. It's for proving anything, but
Yeah, you can say like one line that you could take is that this gravitational models generically gives rise to this Fermi liquid with very finely tuned parameters. So.
While thermodynamics is not showing.
Sorry?
Okay, I will talk to you privately. And if no other questions, then let them to speak again. Oh, okay, yes.
Yeah. Okay, so maybe I missed. So there is a story of temperature dependence of the zero sound parameters. So in this black hole background and also with Gauss-Bonnet, do you know what is happening? Is it
Okay, so in this black hole background, you cannot see the story because basically zero sound. You're not supposed to see at all. So this hydra is supposed to be valid all the way to omega equals 0, basically, because of this parametrical factor. Now the hope is that once you turn on this Gauss-Bonnet term, you will see a region where this excitation will interpolate between the zero sound and the normal sound. And that's, we haven't done it, but yeah, that would be the natural next exercise.
Actually, I have a question. Are there two different modes for zero sound and normal sound in any of these examples, actually?
No.
They're the same mode?
No, yeah, it's the same. Well, generally, in Fermi liquid, what happens with the sound mode is that it interpolates. So for sufficiently small omegas, it's normal sound, and once omega is larger, then whatever, then you get to the zero sound regime. So this mode just interpolates. So that's what Andrei was referring to. If one could see this interpolation, that actually would tell us a lot. At this point where, if you believe the story, we're in the corner of the parameter space where we're not even supposed to see it. But once you consider this high derivative term, maybe we will see it.
But just within holographic models, there's only one sound mode.
Yeah.
And what you call it, because I guess I'm surprised because in the program theories, there is a different mode. There's nothing to do with energy propagation, right?
Yeah.
But that's
right.
So in the probe, you don't really consider the gravitational excitation.
Right.
So
Right.
it's,
Right. So there's no question of it being the same mode as normal sound in that case, because you're not even talking about normal
if you
sound.
could, right? So if you know the full solution, for example,
Right.
miracle, right? Then naturally you probably see the interpolation between the normal sound.
And the zero sound. You think then they would merge together and become one?
Oh, that's
right.
what we expect.
Right.
Okay, let's thank Andrei again.